Hello and welcome. SFU Math 152, Calculus 2. Name's Brenda Davison. This is section 7.5, Strategy for Integration. So this is going to be a much shorter lecture than previous lectures, and this is just really a review of the different strategies that we've seen, and I'm just going to say a few things. There's going to be a whole pile of examples. I'm not going to work through them all. I'm just going to indicate what method and why, and for those of you who are say currently enrolled in a course that I'm teaching at SFU with Math 152, I will post the fully worked out lecture notes here so that you can check and go through as many of them as you'd like. So my recommendation to you is, of course, going to be that you try them all yourself. You use this as good practice for the midterms and the final exam, and then you check your answers against what I will post. But also here I'm going to give some tips and strategies for how to approach it. So what is different here is we have been doing technique by technique. So for example, we did we had a chapter on substitution. So of course you can be assured that all the exercises will be, the integrals that you're supposed to do will be to use substitution. Then we had a section on integration by parts. And then of course all those examples are amenable to integration by parts, similar to say partial fractions. Well, now we're going to be in a situation where we're going to be presented with an integral, and we have our three main techniques. And we're going to have to make a choice about which one to use. And sometimes it's not completely obvious which choice to make, and sometimes you try the wrong choice and you have to back up, etc. So just we're going to point to a few things like that here, a couple of other things about this table, but again, this won't be any new material, and it will be a short lecture. Okay, so here's a table of integration formulas with no constants of integration. You should not omit them. They've been omitted here just to keep this confined to as small of a space as possible. But these are the ones that you should know. Okay, you should, when if for example you see the integral of secant tangent, you should immediately be able to recognize that that integral of that is a secant. So this gives you a good overview of all the ones that we have discussed, and actually a few that we haven't. So I'm going to comment on that. So one thing I do want to comment on just right here is that we have the integrals of the sine and the cosine function. And I just want to remind you that the sine and the cosine function, that is a circle centered at the origin. I'm imagining an angle here, theta, and then this here is the unit circle. So this is speaking to the definition of the sine and cosine function. And then we have the coordinates of this point right here. The coordinates of this point are cosine theta, sine theta, like that. Okay, so, and we have these corresponding relationships between the sine and the cosine. A little bit further down is something that we haven't actually talked about. So we've basically discussed everything up until here at this point. We've also discussed this. We have not talked about the hyperbolic trigonometric functions. They are here partially for completeness, but they are not something to be frightened of. In some ways are actually easier to deal with than the regular trigonometric functions. Anyway, I just want to make you aware of what they are. So I'm drawing here a hyperbola, and this hyperbola is x squared minus y squared is equal to 1. And then I'm taking a point on the hyperbola, which forms an angle here with the x-axis, exactly what I did up here in the circle. And then the coordinates of this point here is the hyperbolic cosine and the hyperbolic sine. So that is what they are. And you can write the hyperbolic, well, you can write them both, but as an example, you can write the hyperbolic cosine as a combination of exponential functions in this manner. And the reason maybe I'm just putting this one here now is because you do see the hyperbolic cosine regularly, and that is if you were to take a necklace and hold it in your hands, say, fix 2 points like that, hold the necklace would hang under its own weight, just given that it doesn't have, this is a necklace with no pendant. It would hang like that. And this shape, it's not parabolic. Actually, this is what we would call a catenary, and that is the hyperbolic So that's a chain, a hyperbolic cosine. Also, you Google this out. You could take a look at the, it looks like this, the St. Louis. This is a really phenomenal, I'm really impressed with this structure. The St. Louis Gateway Arch. It's a freestanding arch that's 660 odd feet high. So it's quite high, 660 feet. It's roughly actually 660 feet this way too, and it's been standing in St. Louis for a number of years. Hasn't fallen down. It's unguided, so there's no guidelines or anything like that. And the shape of that thing uh, is a hyperbolic cosine as well. It's just the sort of upside down version of the chain. So what we actually see with the hyperbolic cosine is the shape that's formed when you have a situation like the chain solely under tension, or we have the shape here of the gateway arch when the force is solely under compression. And architects and structural engineers often use this interplay between tension and compression to design structures that stay standing. So this, particularly the hyperbolic cosine, shows up irregularly in these sort of structural engineering applications. So I mention it here for that reason. There's a lot of analogies between the circular trigonometric functions that we're more used to and these hyperbolic ones. This is there more for completeness. I'm not going to ask you to take derivatives or integrals of the hyperbolic functions because we're not doing very much with them. Okay, so this is a nice table that you should be able to handle all of these by inspection. Okay, so now the rest of this lecture is just a series of examples, of which I'm going to do the occasional one here, but and other ones I'm going to indicate how, and then I'm going to post a fully worked out work that you can check. I just really encourage you to take the time and just go through these and practice. Okay, so here we are looking at some examples from a final exam a large number of years ago now, and what should be done. I mean, so the thing to do is to look at this and say, okay, it's a rational function. That's not hard to recognize. It's a rational function. Immediately, then you're going to go for partial fractions. Partial fractions, and so that we've just had a lecture on that. That is. You know how to do that now, so you're going to go for the partial fractions. When you do partial fractions, you expect to see log functions and arctangents. Those things come up frequently. Okay, so to sort of bear that in mind. Okay, that's the partial fraction example. Okay, here we have a product of two trigonometric functions. So this is a trigonometric let's get that spelled right. Trigonometric integral. And we've seen, again, on a previous lecture how to do this. This one here is odd, so we save one of those and we use the trig identities. So let me just put a little bit more detail here for B. What I'm thinking of this here is keeping the sign like that and then writing cosine squared as 1 minus sine squared, and then there will be one more cosine, and then making the substitution u equals sine x, and then du will be cosine x, and then I can proceed from there, and I'll just give you the answer onto that one. I got 2 out of 35. So that's the trigonometric integral, and then part C is going to be by parts, and it's going to be one of those ones by parts where we end up with the integral back on the same side. The hallmark of that is so we have this here like that, and we see that the sine is going to, when differentiated, is going to become the cosine, and then when the cosine is differentiated, we're back to the sine. So we're going to get one of those situations where we go by parts twice, and we then algebraically manipulate and find what the integral is. So I'm just going to set it up. This is going to be by parts. The way I did it was u is sine 2x, and that made that du would be 2 cos 2x, and the other part of the integral, sine to dv, is e to the x dx, and then I integrate that to get v is x, and then I'm going to go use by parts, and then I'm going to get halfway there, and I'm going to go by parts again, and then I will be able to get the answer, which I will put here. The answer to this integral is 1/5. This integral is this guy here, sine 2x e to the x minus 2 e to the x cos 2x plus a constant. Okay, so by parts twice. Yeah, questions about any of these? If you're in one of my classes presently, then certainly questions during the Zoom sessions are more than encouraged on any one of these. If you just, or you can send me, or you can post, I should say, post on the Canvas discussion board. How do you do, you know, excuse me, question 4, number C, or something like that. And myself or a TA will discuss that with you on the Canvas discussion board. The main thing, I just can't say it more enough times. That is the main thing, is it's just practice. Okay, that's all. So here we're looking at 1. We see that square root of something, the square root of x squared plus something. There's a cube there, but that we're not going to let that bother us. So what we need to do here is do the trigonometric substitution. So whenever I see the square root of x squared plus something or x squared minus something, I immediately think trigonometric substitution. And in this case, the one that I used was x equals 3 tan theta. And then, of course, you may well need a trigonometric identity to go with that, and that would be the 1 plus tan squared is secant squared. So you're also going to need this. 1 plus tan squared theta is secant squared theta. Rather than maybe going through and sort of just getting an overview on all of these, maybe go through this lecture slowly. Maybe you know, you just got some information about part A. Maybe do part A yourself now and check your answer. You can use a Wolfram Alpha to tell you what the answer is too. Maybe do 4 or 5 of them and then take a break and then come back and do some more. Okay, I think just watching this is fairly dull. So, okay, here I see the log function, and I also see the derivative of the log function here. So what is occurring to me then is just a substitution of u equals log x. That will get you what you need to do. I see cos squared. If I ever see just cos squared or sine squared, I'm going to be using the appropriate identity. So in this case, let me just say I'm thinking here identity. And the identity I'm using is going to be this one here. Cos squared x is 1/2 of 1 plus cos 2x. That'll get you that one. I see this kind of a product like this where one thing will get simpler on differentiation. So my immediate thought here is to go by parts and to assign the thing that gets simpler to be differentiated. So that is going to be with u equal to log x and dv equal to x cubed dx. V. Well, then you figure out what du and is and what v is. Okay. So where are we at here? E. Let me just make a little bit more space. What am I going to do for E? I'm seeing it's x times secant squared times tangent squared. So what I'm looking at this, I see, let me just write E down here so we're clear what I'm looking at. That is x secant of x squared tangent x squared dx. So what I'm seeing when I look at this is that I have an x squared here and here, and then I see that basically the derivative of x squared there. So I would let u be equal to x squared, and then du be equal to 2x dx. That will allow this thing to simplify down into this secant u tangent u du, and then I can recognize that from the table. That's when I need to be able to go, oh yeah, that's something I do know. You don't want to be trying to think, oh no, what substitution, what should I do now? No, you want to recognize that as the derivative of the secant function. And then I would back substitute. There we go. Of course, again, you can always check by differentiating. Okay, the final one here on this page, there's a few more of these pages to go. This one here, it's a rational function. The degree of the denominator is less than the degree of the numerator, so I can immediately proceed with partial fractions. Partial fractions. Maybe I won't complete the integral, but I'll just make sure that we can do the partial fraction decomposition. It's going to be it's a product of two linear factors. Okay. I add the fractions and I find that A is 1 and B is 2. Okay, so it's partial fractions. I end up getting two logarithmic functions when I do the integration. Okay, just a few more like this. Some other final exam questions. This one looks like slightly trickier than the ones we've had before. Let us do A right here. So I'm talking about this one here. I see that log. I know I need to get rid of that in some sense. So I'm immediately thinking I want to do a substitution. So I would make a substitution, let's say like this. W is log of X. And then what? Let's see. That means that x is e to the w. And here that means that dw is 1 over x dx. The reason I'm sort of hesitating is because I see, oh, I have this problem here. So it's not gonna fall just immediately on the substitution. I have to be a bit more cautious here. So let me go through with the substitution. And so that's with this substitution, this integral is going to become e to the 2w. That's the x squared. And then the log of x is w squared. And then the dx is e to the w dw. That's dx. Okay, so this then becomes the integral of e to the 3w times w squared dw. Now the good news is the log function is not sitting there anymore, and now I look at this one and I could go here by parts. Well, this is a bit of a trickier one. You make a substitution, it's like, it doesn't sort of line up exactly with, the substitution makes it doable by inspection, but what happens is you do the substitution and then it is doable by parts. Okay, so that one's a bit trickier. Let's look at B. It's some type of trig stuff happening here. I'm seeing I've got an x here and I've got a 2x there. That bothers me slightly. So I'm thinking I should potentially use the this identity here, sine 2x equals 2 sine x cos x. That will make my integrand look like this. Cosine, I get cosine cubed from here, and then I got another cosine there, so I'll have cosine to the 4, and there'll be that 2, cosine 4 to the x times, I've got the sine here, sine x dx. And then I can make a substitution, u equals cosine x, and du is minus sine x dx. And then the whole problem will be easily solved. You remember, of course, when you do a substitution, you must change these limits. So substitute completely. That is a mistake that is easy to make. You forget to change the endpoints of integration during your substitution. Yeah, and then you get the wrong answer, and nobody's happy. Okay. What about C? looking at C. I'm thinking to myself, what should I do? Well, then just algebraically simplify. It's sort of written out in an annoying manner, so you can just multiply that x to the 1/2 in, and you're going to be able to simplify that to this thing here, 3 over x minus 1. So it's just a manipulation of the integrand. That's nice, and then that's easy to handle with by inspection. You see that that's a log function. Okay, D. What is D? See what method we would be using there. I see that square root x squared minus 1, so I immediately think, that is a hallmark of needing a trigonometric substitution. Which one will it be? I can look back to the chart, and you will see that to do this one you need x equals secant theta. I'd be thinking in my head, what is the derivative of the secant? That is the secant times the tangent. Okay. The better you can have the derivatives in your head, the faster and more accurately you'll be able to handle all these trig functions. Okay, let me just write out the answer for this one. The answer for D is, so you can check, is square root of x squared minus 1 minus arc cos of 1 over x plus a constant. Okay, that's E. What is E? It's a clear example of partial fractions. I'll even just write that up here. You can easily see what to do. This is integral from 0 to 3, and it's going to be some number a over x minus 2 plus b over x plus 1 dx, like that. So you need to figure out what is a and b in order to do this, but I was just about to say, and then you can evaluate it at the endpoints, but we need to be very careful here, actually. Something is coming up. Let's spend a bit more time about this one, actually. We haven't actually covered this yet, so I'm going to say not so much about this. We are going to see this coming in a future lecture, but I see it here. So let me just actually say a little bit more. Okay, so I'm going to just make a note of this here, right here. Caution, danger, right here. Caution, danger, caution, danger. Why am I doing that? Because this thing actually becomes undefined at x equals 2, and x equals 2 is between these two numbers. So you're actually integrating across, and at some point when you're integrating across, when you reach 2, the function that you're integrating becomes infinite. This is a situation that needs to be taken seriously, and you cannot just blindly proceed. So we haven't seen what's going to be called this is actually an improper integral. We haven't seen this yet, so no worries that we don't know how to do this yet, but certainly, in fact, sort of when you're doing stuff, you want to be thinking to yourself like this all the time. Okay, I'm proceeding along. Are there any sort of obvious potholes that I'm going to fall into here? Are my functions defined? What domain am I looking at? Those kind of things. Am I taking the square root of negative numbers? Am I taking the logs of negative numbers? Am I dividing by 0 when I'm and then not noticing? So you want to have always your sort of your antenna up, say, for things that could be potential things that you can do that well, makes you look like you don't know what you're doing. That's to be avoided at all costs. So let me just say a little bit more about this one here, with the assurance that we're going to come much more to a full lecture about how to handle this situation. So it's just that I guess this was on an exam when we chose these examples, and so let me just write it here. It is here now, so let me just say this about it. A preview. Yeah, this is what is coming, just like a movie preview. So let me finish the partial fractions so I can just talk about this. This is 1/3 dx over x minus 2 minus 1/3 over x plus 1 dx. Okay, who cares about this? This one, I mean, this is some number. We can easily do this because x plus 1 is always will x plus 1 will go from 1 to 4 when x goes from 0 to 3. It's this one that we have to be careful about. Okay, we have to take a close look at that. So what I'm saying is x minus 2 equals 0 when x equals 2, which is in 0 to 3, which are our limits of integration. So we have what we call an improper integral. So that's this. Okay, so how we do this, what we do, I'm just going to write this down again. I will get to this in more detail, but we are going to rewrite this in this manner. The limit as t approaches 2 from the left of the integral from 0 to t of 1/3 dx over x minus 2 plus the limit as x approaches 2 from the right of the integral from t to 3. So we're basically dividing the integral into 2, and we're dividing it exactly at the spot 2 where there's a problem. And then we're going to take the limit as t approaches 2 from either side. And we're going to add those two things together. And in this case, we are going to find, in fact, that, so now what we can do is we now have an integral that's legal. Both of these are legal because between 0 and t, the integrand is defined, and between t and 3, it's defined. So we're able to go ahead. So we go ahead, and then what we do is we take this limit, and what you'll find is that well, if we have problems with either one of these limits, then we conclude that this integral diverges. So in this case, we will have a problem here. This one here, 1/3 dx over x minus 2. So I'm going to just go ahead and integrate that, just keeping that limit out in the front. That will be 1/3 of the log of x minus 2. And now I imagine hang on. This is going to be a t. I imagine the integral. I imagine taking this limit. We're into a calculus 1 problem. This is it diverges. Okay, again, we're going to come to this. We're not there yet, actually. Okay, but that is one of our questions. Let's keep going. We got a bunch more questions here. For these ones here, I am simply going to indicate the method. Again, stop doing them yourself, and then if you did it by a different method, no worries. That is sometimes possible to do them by more than one method, but do them and then see if you can't do them, come back and see what tactic to try. Okay, so in this case, I used a substitution and then by parts. So I had to use two different techniques, one after the other, and the substitution I used was w equals minus x cubed. Okay, and then I got integral I could do by parts. Okay, part B. Well, there's a variety of different ways of doing this. One is to notice, like we did early on, area of a circle. Okay, so it's half of a circle centered at 3, 0 with a radius of 2. So that can get you what you need. The other thing, if you don't notice that it is that, then maybe the thing to do is a trig substitution. So two possibilities. This, of course, is going to be much faster if you notice that. So really, sort of paying attention to the function here, like what function this is, and what it looks like is a good strategy. Okay, next, what is this one here? Oh, we haven't really seen what to do much here. something that looks like this. Let's take a little bit more of a look at this one. C, the integral of the square root of 1 plus x over the square root of 1 minus x. Okay, so what to do here? It's not so obvious actually, but what you can do is multiply by the conjugate, like in this manner here, where this is the conjugate of this. So that is a tactic that will work, and that will lead you to, so I'm multiplying by 1. Do not I said it, do not underestimate the power of multiplying by 1 in a variety of guises, or adding 0 in a variety of guises. It's amazingly effective a lot of times. Okay, so that will transform the integrand into this, 1 plus x over square root of 1 minus x squared dx. And once the integral is transformed like that, then you can do a trig substitution. Let me say that it is easy to make integrals that are very, very difficult to try to evaluate. I sometimes am sitting in my office hours and somebody will come and they'll just sort of plunk down a thing and say, how do you integrate this function? And no, most of the time I can see how to do it. And sometimes I start to look and I'm looking and I start to sweat and then I'm like, oh no, I don't see what's going on. I don't see how to get at this. And every now and again, I will sweat it out for maybe, I don't know, some length of time before I give up, and I think, okay, I'm just going to look up what the answer is so I can see where I'm going to try to hopefully get some insight. And when I go to do that, I find out, oh, this function doesn't, I actually can't find the answer in terms of elementary functions. So sometimes you can't even tell whether it's just because you haven't seen which way to go, or whether there in fact isn't a function that has an elementary function that works. So I recognize that it's not always obvious to see which way to go, and I don't actually see a necessity in testing you that there's no requirement for me to make these things kind of really tricky. So if you don't just see the, you know, a clever multiplication followed by the right substitution followed by that you can't get it. Mostly what I want to and I will test is, do you understand the main methods of what we're doing? Can you make a substitution? Can you do integration by parts? Can you do partial fractions? Do you know how to handle the endpoints on the integrals, etc.? So I will, to the best of my ability, not make it too difficult when I test this. I would consider this one to be quite difficult. Okay, D is this one. D here is you see the derivative of the sine function sitting in the numerator as the cosine, so this is clearly going to be a substitution. And this one here, that is going to be a trig substitution. Okay, so that's yet another page of those things for you to practice. And again, I will post fully worked out solutions for you in our Canvas container, and you will practice. The more you practice, the better it is. Okay, that's all for this lecture. I will be back for our next topic, which will be approximate integration. Bye-bye.